So in our previous class we have discussed about Why principle and Pauli exclusion principle, as well as the energy of the orbitals. Now we come to the next one, Hund's rule of maximum multiplicity. So this Hund's rule of maximum multiplicity, it talks about filling of electrons in the orbitals belonging to the same subshell as P, D or F. So the energy in that subshell will be degenerate, okay, that means of similar energy. So according to this rule, Hund's rule of maximum multiplicity, this rule states that pairing of electrons in the orbitals belonging to the same subshell as P, D or F does not take place until each orbital belonging to the same subshell has got one electron each, that is, it is singly occupied. So according to this rule, in an orbital the electron will be singly occupied in each subshell. Let us see some examples for better understanding. For hydrogen has only one electron, one s1. So hydrogen has only one electron, okay. So in a neutral element, okay, number of proton is equal to number of electron. So for hydrogen containing one proton, it has one electron, so it has s orbital, okay, one s orbital. So it will have only one electron, and this electron we can represent it like this, okay, one arrow pointing upward. For helium, atomic number 2, therefore 2 electron will be present, so one pointing upward and one pointing downward, okay. So this is according to Pauli exclusion principle. So in this one is s orbital. So in an orbital, electrons, to a maximum number of electron will be 2, and they should be in opposite spin, okay. So one pointing upward, one pointing downward. Next one, lithium, atomic number 3. So first this subshell will be filled, okay, first singly, and then after that pairing will take place, okay, like this. And then after one s orbital, what come is 2s orbital, okay. For lithium, 2s orbital will come, so it has 3 electrons, so 1 electron will come here. So for better, let's point it like this, okay, arrow, for better understanding, one arrow pointing outward. Next is beryllium, atomic number 4. So first case, s orbital will be filled, okay, or paired, okay, with 2 electrons, and 1s orbital paired, 2s orbital. For lithium, okay, it is like this, and then 4 electrons, so it will be in opposite spin. Next is carbon, okay, this will be same for carbon. So carbon, atomic number 5, so 2p orbital will come, so 2p has 3 orbitals, okay, represented by this 3 box like shape, okay. So 1 electron will come here. Now for nitrogen, 6 electron will be there, atomic number 6, so hydrogen, helium, lithium, beryllium, this will be boron, okay, not carbon. Hydrogen, helium, lithium, beryllium, boron, okay, boron. 1 2 3 4 5. Next will be carbon. Carbon. So in this case, pairing will not take place, okay. Pairing will not take place, okay. This is s orbital, so for s, pairing takes place, okay, since it has one orbital, but for this case 3 orbitals, so it is first singly filled like this, okay. So carbon has 6 electrons, so according to this rule, it is singly filled. Now after carbon, oxygen, nitrogen will come, nitrogen. This thing will remain the same, singly fill. So this will singly, we need to fill it singly, okay. So if we fill it like this, then it will be wrong. Now oxygen, atomic number 8, so 8 electron will be present. 4 5 6 7. So after each electron is singly filled, only then pairing will take place, okay. Each electron is singly filled in each orbital, after that pairing will take place. Next is fluorine. First singly filled, okay, pairing takes place. So fluorine atomic number 9, so 9 electron. 4 plus 5 9. Next is neon. First singly fill, okay, and then pairing. So for neon it is completely filled. So this rule tell us that electron is first singly filled in its subshell, okay. 2p subshell has 3 orbitals. For s we write singly and then after that pairing, okay. And for this case also singly fill, after singly fill pairing takes place. So the next topic is electronic configuration of atoms. So electronic configuration atoms, here we are going to discuss about the electronic configurations, okay. So in this electronic configuration, what we are going to do is we'll discuss about off-by principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. So all three combine and then we'll discuss this concept. So this one is from off-by principle. So this is from off-by principle, okay. So this figure gives us the order of filling of orbitals, okay, according to the energies, order of energies, okay. We have discussed this before also, so we won't discuss into much detail about this. So now let's come to electronic configurations. So we know s orbital, okay, 1s orbital, 2s orbital, 2p orbital, 3s orbital. So s orbital, okay, it has got one orbital. So according to Pauli exclusion principle, for s orbital only 2 electrons will be there, okay. p has 3 orbitals, so altogether 6 electrons will be here, and d orbitals altogether 10 electrons will be there for s. Okay, and f, for f altogether it has 7 orbitals, so altogether 14 electrons will be there. So f, for f we have not I've not written here, okay, but let's discuss this, and if you understand this one, you will be able to solve for even for f orbitals. So hydrogen has 1 proton, okay, for neutral element, number of proton is equal to electron, okay. So atomic number is equal to the number of proton also. So these are arranged according to atomic number. Okay, this atomic number or number of proton will be equal to the number of electrons. So altogether up to from 1 to 30. Okay, from 1 to 30 I've written here. So we're going to discuss on how to write the electronic configuration. For hydrogen, 1 electron, so it will be written as 1, and in s orbital how many electron will be there? 1 electron. Okay, 1 electron, so we write it like this. So 1s, for 1 electron we write it 1s1 to represent 1 electron is present. For the second case, helium, 1s2, 2 electron present, so first it will be filled. Okay, as subshell will be filled according to Hund's rule of maximum multiplicity. Now for this one, 1s2, okay, 3 electrons, so 2s1. Okay, in s 2s 1 electron is present, so we'll write 1 electron like this. And then for beryllium, 1s2, 2s2, so 2 electrons come here. Okay, pairing takes place here in this subshell. Boron, 5 electron, 1s2, 2s2, 2p1. So 2p1 singly filled first. Okay, so this first may represent 2px orbital, 2py, 2pz, okay, orbital. For carbon it will be like this, according to this, okay, of by principle, 1s followed by 2s, and then 2p, 3s, okay, and then 3p, like that. So we have done for 1s, 2s, and then after 2s, 3p, 2p, sorry, 2p, 1s2, 2s2, 2p, 2 for 6 electron. Okay, so here 6 electron present, 2 2 2 6. So first we will fill it singly. Now for nitrogen, 1s2, 2s2, 2p, 3 singly fill. Okay, 1s2, 2s2, 2p, 4. So after singly filling, the next electron will be here, 1s2, 2s2, 2p, 5. So the next electron will be here. Okay, after the pairing will take place, 1s2, 2s2, 2p, 6. So all are paired. So p can have 6 electron, up to 6 electron. So accordingly you can fill up the p orbital. Okay, so if you write 7, then it will be wrong. So up to 6 electron p orbitals can have. Now for sodium, okay, 1s2, 2s2, s can have maximum of 2 orbital, 2p, 6, After 2p, what come? S, 3s. So 3s 1. So altogether 11 electrons. So the next electron will come here. And for magnesium, it will follow the same sequence, 2p6, 3s 2. So these two electrons comes here and pairing takes place in the same subshell as subshell. Or you can write this in short form. Since this neon has 10 electrons, okay, so simply we can write or, okay, or Ne 3s2, okay. 6 plus 4 10, so this is also 10. What remains is 3s2, so in short form we can write it like this. So let's write this in short form. Neon 3s2 13. So the next orbital will be after 3p 4s come, okay, 4s. So for after 3s 3p will come, sorry, 3s na 3p will come. So 3p 1, so this one will come here. So this will 2px, okay, like this, in this, like this only, okay. Neon 10, 3s2, 3p 2. So it will follow the same sequence, okay. 3s2, 3p 3, 3s2, 3p 4, 3s2, 3p 5, 3s2, 3p 6. So it is completely filled, okay, it is completely filled. So after 3p 4s come, okay. So these are arranged according to the energies, okay. 3p 4s come, and then after 4s 3d. So that means 3d has higher energy than 4s, okay. So for this case, instead of 3d, 4s will be filled up first. Three s2, 3p 6, and then 4s 1. So we can write 1 here, yeah, 1 electron. And E 3s2, 3p6, 4s2. So we'll fill this as orbital, okay. So atomic number 1 to 20 is important, okay. So you memorize this atomic number, okay. Firstly up to 1 to 20, okay. This will help you in solving some questions, okay, if it is asked in exam, and then it will be helpful, okay, for you even in further study. So this is the basic, okay. If you understand this, then you will be able to solve, okay, many questions, and you will it will give you a better understanding. So let's do for atomic number 21. So here argon is completely filled. Okay, so argon has 18 electron. Okay, so for this one we'll write in shortcut. Okay, or we can write, let's us first write in the long form: 1s2, 2s2, 2p6, 3s2, 3p6. So 10 plus 4s2, 3d1. This becomes 21. So in actual case, this usually 3d is written before 4s. Okay, so we can write 3d1 and then 4s2. This can be written in short form. Okay, AR 18. After that 3d2 4s, this will be 1. Okay, and 4s 1. So we can write the 18 and then the outermost valence electron we can write afterwards. So this will follow the similar sequence: 3d2 4s, this is 2, 4s2, (3d1, 3d2), this will be 3d3. Okay, so for 3d1 let's write here 3d1, 3d1. For 3d2, okay, I forgot to write here. For 3d3 let's write here, so it will be singly occupied. For chromium, okay, for chromium we will see a different case for chromium. Okay, actually it is supposed to be 3d4. Okay, 3d4. After 3d1, 3d2, 3d3, 3d4 it will be, but for chromium it is 3d5 and 4s1. Let's see here. So in this case 4s, okay, 4s will have 2 electron. Okay, and this 3d, actually it will be 3d4, 3d4. Okay, but 3d and 4s, okay, they have almost, or they have similar energy. The energy difference is not much, okay, between 3d and 4s. So due to this reason an electron from 4s can jump to 3d orbitals. Okay, and this becomes a single electron. Okay, 4s, or 4s become half filled. Okay, so these fully filled half filled orbitals, okay, are stable. Okay, stable, that means they are symmetry, they attain symmetry. Okay, so half filled and fully filled orbitals, okay, half filled and fully filled orbital, they are stable. And even for this one, as with single electron, we can say it is also stable, because since it is half filled. So usually these orbitals, they will try to be stabilized, they tend to be stabilized, and therefore this electron jump here, to get stable. So for chromium it will be 3d5 4s1. Now for manganese, we are 3d5 4s2. So for chromium it will be one electron will be missing, here, and it will jump here. Two. So after chromium, for manganese, we can add one electron here. Chromium, one electron missing, and 5 electron will be in that d orbitals. So after chromium, manganese, for manganese we can add. This will become 2, so we add one electron here. For iron, 3d6 4s2. So pairing will take place. For cobalt, 3d7 4s2. Pairing will take place. For nickel, 3d8 4s2. Pairing will take place. For copper, Ar. So for chromium and copper, for copper also similar case happens. Instead of 3d9 to get stabilized, it becomes 3d10. So from 4s2, one electron jumps to d orbitals and it becomes fully filled. This becomes 4s1. Now for zinc, Ar 3d10 4s2. So this is the electronic configurations. So this is how you will fill the electronic configurations. So let's discuss a few concepts. Stability of completely filled and half filled subshells. So we have discussed about this before. P orbital. So this is p orbital. So electrons are singly filled. So this means they are half filled. So in half filled, what happens is there are 2px orbital, 2py, 2pz. So in these half filled orbitals, there is equal distribution of electrons in these orbitals, 2px, 2py, 2pz, and therefore we call it as symmetry. So they attain symmetry. So since they attain symmetry, they are stable. We know that electrons repel each other, and they are not stable. So they can shift from here to here, from here to here, and this one from here to here, and this one from here to here, in the same subshell, or we say they have degenerate, or they are degenerate, having similar energy. So this is also the reason why they are stable, due to symmetry, or they can exchange energy, or they can shift, within the same orbital, okay, in the same subshell. This is also in case of fully filled orbital. So in this case we see pairing, okay. So for fully filled orbitals, they are also stable, okay. So some example of those orbitals are P3. Okay, P3 is half, okay, and P6 means fully filled, okay. D5 means singly filled. So these are half filled, okay. D10, so fully filled. So fully filled orbitals and half filled orbitals, they are stable. F7, so 7 orbitals will be there. Half filled, they are stable. F14, so 14 electrons will be here. Fully filled, they are more stable. So this explains the stability of these electronic configurations, okay. So please remember, half filled and fully filled orbitals, they are more stable.